live demo in this presentation. Hopefully that'll go well. That'll be toward the end. I hope you enjoy this. If you have any questions, just shout them out. I can answer those. So this project started back a number of years ago. And the goal was, as we're testing IoT and start thinking about IoT, and we start looking at the technology outside of the normal type of hacking and tacking and testing that we would do, how do we deal with devices when we're examining or testing them for a customer or doing research? When we start thinking about how an example of the device would be a device that would do Bluetooth. So you have a Bluetooth device and it communicates to the cloud. How does it communicate to the cloud? It has a bridge of some type that'll connect it to Ethernet or Wi-Fi. So the basis of the research is if you're dealing with a device that has good security out to the cloud and it has pretty good security to the Bluetooth, it's all encrypted, how do you really know what's going on? So I started thinking about this. Well, what about inter-chip communications? Often we have multiple microprocessors that are built into IoT technology and they communicate with each other. An example, Bluetooth, low energy, typically communicates with UART between the chips, and it can communicate mostly up to about 4 megabits per second, but they rarely do it. Often it's pretty low, 115/200 or even down to 9600 in some cases. And this, by examining the inter-chip communication, we can get to a point where we can get a really good understanding of what's going on within the end-to-end security. And then we expand it out, and we released a proof of concept tool here about a year ago, and we're going to cover some of this stuff with the goal of, now we can see the inter-chip communications, but how can we manipulate the inter-chip communications? So we built a tool that we're going to talk about that basically, it's early stage of it, it's proof of concept, but it is a proxy. So we're going to talk about that, and proxy communication between microprocessors on the circuit board. Again, if you have any questions, don't hesitate to ask. And again, why we're doing this, gather that knowledge, build the information, really understand what we're looking at. So, and the target focus I had mentioned was in reference to a BLE device for the most part. This will work on other technologies, and you can also do inter-chip communication analysis, doing SPI, UART in this case, I2C, or any other communications that may be taking place. This is just a focus on that particular version. We plan on expanding it out to other things. So how does this typically work, or the environments we see this in? We have, in this case, we're talking BLE, and we have like a Wi-Fi, and we may have a main CPU. So you could have multiple CPUs on a board, and all of these are communicating together. You may have one that's just BLE and Wi-Fi, and then you may have one that actually goes into Ethernet from the BLE also. So you have multiple environments that you can encounter. And in some cases, and we're starting to see more and more of this, you may have everything on a single system on chip. Cases like that, not a whole lot you can do for inter-chip analysis and actually tap into the circuits, which is way more complex, and I haven't got to doing that yet. Be nice to do. I don't have those tools or the money to do it. So identifying chips. So one of the big things is getting inter-chip communications is getting into reverse engineering the actual circuit boards. What are the processors? What is the communication path? What are all of those components? You can do this through visual data sheets. You get the data sheets, you look at them, what's the processor, what's the pin out of the processors, to get a good understanding. You can use a multimeter. Multimeter, so it's ringing out. It makes a buzzing noise when you get a short and go through the circuit board and try to figure out where everything runs on that circuit board. Is it a two-layer board? Is it a multi-layer board? How do we deal with that? A gentleman named Damien Coquel out of Paris did a great presentation, Hack in Paris, where he talked about photo overlay of the board to actually map out multiple layers through the vias, through the circuit board as part of this process. And it was a real good discussion on that particular topic. So here's a couple images of some of the stuff I did in reference to some research, not with this research, but other research on mapping out circuit board structures. This happens to be an actual board associated with cellular communications, which is some of the research I have been doing. And in one case, not this one, I was actually paid by one of the big vendors to actually tear down one of their circuit boards and actually reverse engineer all this to try to identify how to identify tapping into that circuit board. Is your board vulnerable to tapping into inter-circuit communications? And what we did in this case here, we literally threw the board in an oven, heated it up, and I took a brush and just wiped all the components off of it. Stripped it down to the bare board and start tracing everything out that way using data sheets to map out all the circuits on the board. And in one case, I was working on something a little more complex where we're dealing with a SAM module, which is a security module. Security module is only 12 pins, and I literally started delaying the board under a microscope, bringing down the layers of the board, trying to figure out where all these runs were since it was a multi-layer board. In this case, they actually thought through this whole process and the potential attack vectors. I was never able to successfully do it. I ran out of time limiting everything, obviously, but I made it down to like 3 layers there. And that's what we're seeing through 3 layers. And I just did this with a scribe, actually scraping the circuit board as I went down. Just give you an idea of that whole footprint there is that chip. So you can see it's a pretty small area. But I've done this a number of times, even in this particular project where I had runs that were running through lower multi-layers. And I didn't have an X-ray machine or anything like that, so it was literally picking spots on the board where I thought the runs would go and start delayering the board until I found the tap points on the circuit board. So let's go ahead and look in examine the inter-chip comms. This particular case, in this example here, we actually had a lock. This is a smart lock, a Brelong, and it has a BLE and a Wi-Fi module that we wanted to look at. So we needed to be able to tap into this. So as we started digging into this, is what the circuit board looked like, and you can see we have 2 modules on here. One is a Wi-Fi module, and the other one is the actual Bluetooth low energy module. So we wanted to figure out how can we tap into this thing safely, where all the runs going. So if we blow this up and look at it, we can see coming off the BLE module, there's a transmit receive for UART that connects to the actual Wi-Fi module, the expressive Wi-Fi module. But in this particular case, and the reason why I put this one was kind of unique, instead of a straight run through, we actually have resistors that are in line. They're not pull high, pull low type resistors. They're actually in line. And these are impedance matching resistors because if you connect the devices, these 2 modules up, they won't communicate. So if we need to tap into inter-circuit communication to do this, you got to be careful where you tap in. Since there's an impedance issue there, if you tap into the wrong side of the actual resistors and try to do anything weird, you'll load the circuit and actually cause communications to halt. So we found out in most of these cases here, all the cases where I've encountered this, you want to tap into the transmit side of the communication. Remember, we have communication going both ways. So there's transmit going both ways, just transmit, receive, just what direction it's going in. So in this case here, we want to tap into the circuit, so we want to do it between where that TX is and where that resistor is, very small space. I started thinking, hey, let's just redesign the board slightly and make this a little easier. So what we want to do is as part of this whole process, since we want to get inter-chip and we want control of inter-chip comms, we need to either tap in, we need to break the actual circuit runs, and we need to do it on the transmit side on each side to do that of the resistor to make this effective. In this case here, what I did was I just removed the resistor. I hooked my wires up so that I could handle the transmit-receive structure out to my FTDI device. So now that I've removed the resistor and I need to put it back in the circuit, so I traced out the runs. The yellow side marked there is where the vias passed through the actual board where the resistor was removed from. And the other side goes back through the board to the ExpressF module. So in this case here, what we did was we actually cut the runs where we want to tap into it, and we put the resistor in circuit there. So we add the resistor in there, and then as you notice up here, I didn't cut the run yet here. We are going to cut the run and tap into it, But the reason why I didn't was I knew for sure if I cut both those lines, I'd end up soldering the resistor in the wrong spot. So I made sure I didn't cut both of them at the same time. But then we went ahead and cut the run here, and we can see it, cut the run here, and actually put the other wires in there and tied this into our other FTDI device. What we actually did was we cut the runs, route all the communication off to a breakout board. From there, we can open and close the circuit at will, tap in with whatever test equipment we want to do. So if we want to halt all the communications, we just turn the circuit off. Now we can potentially inject stuff in. This is how we started off early on in this particular project, but we took it to a new level later on, and we'll actually talk about that later. In this case here, I did most of the testing very manually. I hooked up some FTDI devices. So this is how we tapped into the two FTDI devices. And then I was able to catch the communications, open and close the circuits with a switch, transmit and receive data or manipulate data inside the circuit. So in this particular case, go ahead and look at what we started capturing. So we started to capture, this was like open the lock. We send a command, open the lock. This is a command to close the lock. These here are the actual responses back on the TX side on this thing here. Interesting, in this particular case, I don't know if it's on the next slide or not. This kind of breaks it all down. So we have a frame header. Remember, we're not dealing with a UART communication that is human interact UART. So there's no actual end of line, return carrier, none of that stuff is actually interchip comms. So typically you're never going to see that, nor are you going to receive anything that's readable like you would typically see on a serial connection that you have. We also found out that this is the actual MAC address encoded, which is kind of weird. So yeah, a MAC address would be 6 bytes. This is actually 8 bytes. So they actually encoded the actual MAC address of the Bluetooth device that it was communicating with into an 8-character code encoding. This initially was unknown, and then at the end we have a CRC, which is quite common for how you see interchip communications most of the time. Again, as we look at this, we see that open requests, and these are the responses back. But the responses back in this particular case actually return the true MAC address of the Bluetooth device. It's always going to be in the communication. This kind of screwed me up because most of the devices I see, the request command going out will usually have MAC address in it because it has to know the device that it needs to connect to at the end, so that communication has to be there. You may see devices that have multiple endpoints, Bluetooth endpoints, or various other communication protocols that it's going to have to communicate to. So we know that encoding equals that MAC address. So as somebody who wants to inject data and maybe tell this thing to talk to somebody else's lock or do something strange, we need to figure that out. So I literally went through and fuzzed it. And my initial finding was that if I increment that encoded by one byte or 1 byte up, it would actually error out, and I would just get an error response from the BLE device. It had to be incremented up 2. That's why you see each one of these increment down by 2 in this particular case, and it equated to those MAC addresses so you can see which one. This is a small sample. I went through and did this a lot, hundreds and hundreds and hundreds of these, and then I went sniping at work. I found a developer who was bored one day. I'm like, hey, dude, you like puzzles? I got a puzzle for you. It took him like a week. He didn't use company time, but his spare time, like a week. He came back to me and actually developed a program and figured out the encoding. Now, he explained it all to me. It wasn't 100%, but it would encode 90% correctly. But it was like this encoding was weird because he turned it all of this into, instead of hex, he turned it all into raw binary and then started working on patterns on the binary part of it. And it turned out it would build blocks of data in the binary and then bit flip it. Blocks, then bit flip it. and it had a certain sequence of bit flipping to actually work. So praise to him, he did a good job at it. So that gave us a way to actually monkey with the MAC address, figure out what a MAC address would be. So we started looking at, can I target other devices? And it turns out that there is a, before we get into this, that part that was unknown, this section down here. For each lock that's actually configured in the system, that open-close command, that block never changes. So think about that. Once this is keyed, once your device is keyed into the system to the cloud, it never changes. So there's no encryption, there's no encoding, there's no nothing. It's always the same thing. So anytime that's played in the circuit, it would actually carry out the operations, whether it legitimately came from the cloud or not. The determination was, and we didn't have enough samples, but we determined that more likely that is actually a salted encoding of the device's key address. You know, when you configure a device, they have an address or a number on the back of them. So when you configure it into your IoT function, whatever it is, that's usually a secret that you have, no one else should have. We figured out that this was probably the same encoding, but we believed it was salted in some way. We didn't have enough test samples to figure that out, but we did some other weird testing just to see how the system would work. I decided to go, this particular device only allowed you to configure one lock on the other end of it, just one lock. So I decided to keep the cloud out of the thing and try to pair that other lock in through injection. So we were able to take data off another device we were able to gather. And what I did was, this gives us the ability to remove an actual lock from the whole bridge environment. This gives us the ability to add it. So we started off by adding and re-adding it back in to see if we could control the device's configuration. And then I took data captured from another device, even though this device wasn't supposed to talk to more than one lock, and I injected it in for the other lock into the system and programmed the system to talk to two locks. And then it came down to whatever MAC address I sent, I could actually control that lock. That lasted for like 20 minutes, and then the system reset itself, got rid of the old lock, the first lock in, and kept the new lock. Interesting behavior. So this is some of the behavioral testing we've done, trying to figure out how a device handles security. In this particular case, once a device is configured, the key coming from the cloud, or the command coming from the cloud all the way to the lock, never changes. It's never readdressed, never rekeyed. It's always the same. So if that data is compromised, obviously the level of compromising here is way complex because it's inter-chip related. But it's always tied back to the actual device's key that's on the device. So the next time you go to cut a YouTube video on a new device you just bought, for God's sake, don't hold that thing up to the camera so someone can see your key. Here about a month or two ago, I spent one day just going through YouTube videos, recording the number of times I was actually able to get the keys off people's garage doors, locks, all these type of things. As you can see, this never changes. I did another lock. It did change. Turned out it was salted with the actual timestamp. That was it. And that was in the data stream too. So literally no security at that point. So once the lock's compromised, it always comes down to somebody taking the time to figure out what that encoding is. And we know more likely it's the same as this 8-bit coding. Very likely. And if that's the case, if I got your key with enough time, I can make my lock talk to your lock and control your lock or your device or your camera or whatever it may be. So something to think about from that particular direction. Yes?
On that data stream, is that like a Wi-Fi, a Bluetooth data stream that you're capturing?
No, this is all UART. This is a universal frequencies transmit. So it's actually inter-microprocessor communications, which is the raw data. It gives me a chance to look at communications on a device without having to worry about the security on either end and see what's actually going on and how the mechanisms are actually working. So some of the things we're trying to figure out around this, observations, there is required BLE pairing. And I've actually made, in another device that I was doing, another product lock, which I actually did for a vendor. I was actually able to force through interchip communications the device to pair to someone else's lock. Obviously, they fixed that, which drove me to dig into some other locks to see if other people were having that problem. Encoding communication, but it's the same key. It never changes. It never expires. So we get that level of observation. So now we got a better understanding of end-to-end security, and we can start thinking about other attack vectors that could take place at that particular point external to the device, or weaponizing a device. And we don't really think about that. You think about, hey, I'm going to attack their Bluetooth. Now I'm going to attack their Wi-Fi. How about I just go down to Lowe's and buy one of these devices and rewrite it to attack everyone's device? And potential to do that is actually there. So now we have a demo of the tool we created. You can pronounce this in a number of different ways. Akheron, I usually go Akheron proxy. It's for UART interchip comm proxies. So where we got the name, you always got to come up with a cool name. So Akheron is a mythological Greek river. Out of the 5, it is the only one that flows from the mortal world to the underworld, and it's used to ferry the souls of the dead to the underworld. So I thought it was a cool name. So I created a whole bunch of development testing scripts to validate this proxying function. Got most of them working, but I thought, hey, I'm not a developer. It's going to look like a total piece of shit. Let's go ahead and see if I can wrangle in some people. So I had a couple people help me. Matthew Kino and Pierce Berry, both of them were at Rapid7 at the time. Pierce has moved on and is working for HD Morse Company right now. But Matthew's still at Rapid7 and is still helping with this project. We're actually making some changes here last week. So what we're actually going to look at is garage door opener, and it has a BLE sensor. So we have a sensor. This sensor basically says, hey, doors closed, doors open. Mounts on the garage door. It's a retrofit system. So we wanted to see how this communicates, and I picked this as an example. Often when you get into interchip comms on UART, it can be really noisy, like a lot of freaking traffic. This one's a little more simple for demonstrating this tool. It's noisy, but not anywhere near as noisy as some of the devices that we actually run into. And the way Akheron proxy connects in is like we had that sample before with the 2 FTDIs. We actually put software between these two and control all of the interchip comms from both microprocessors. We're going to do this as a live demo here in a minute, and hopefully it works. Hopefully everything's working here. If not, I got a video and we'll walk through there. So let me end this right here, end this show. And we're going to jump over here. Hold on, where's that? I just want to give you a picture of this. Is it in focus? It's vaguely in focus. Of course, it doesn't want to be in focus. Okay, so here is the primary. This here is the primary CPU. Here is the BLE CPU in this particular case. What we have here is the 2 wires hooked up on one side, the 2 wires hooked up on the other side. The run underneath the board here, come up over here where we connect to, and then you run across the board from here to here. If you see those 2 little specks right there, that's where the actual circuit board was cut to reroute all the traffic over to this other device. So now we're going to see if we can get this thing up and running. Okay, so Akheron proxy has a number of functions. Let's go ahead and help so you can see all these. We have the ability right now to actually put this in listening mode so we can capture all the interchip comms on the device. We also have the ability to capture We'll track it in real time. We also have the ability to replay. And release the data in flow. Right? This gives us a chance if we want to MAC edge in a replay, we can go ahead and actually change, saying, hey, anytime you see this MAC edge, just change it out to this and replay. This is early in the beginning of the so let's see if we can get this plugged in. Dying on me? Okay. Yeah, it's working. I got it back up here, okay? Okay. Sorry about that. Try not to clip it on my mustache. Noisy. So the first thing is I plugged in one side. We have a command called list. It'll tell us what are actually available in the USB for the FPIs, and then that one's up. I just make sure that they come up in the correct order. So now we have both of those. So at this point, we can go ahead and so we can set port A. A happens to be the actual primary CPU. The baud rate's 115/200. We define which side we're coming from. We set that up. And then B, which is on the other ADI device. And then we can go start. That'll actually start passing all communications between the FDDI device. And then we can go watch mode. Now I turn it on to see if it actually works. And then I also need to put a battery in this device so it'll come up properly. And then we also have the cloud services on the other side. Shows the door disabled or not running. So we can see it goes A to B, B to A. We can see all the communications back and forth between the microprocessors. It'll take a little bit. There's a number of this thing screaming at it, going, hey, what's going on? I ain't seeing stuff, kind of booting back up. Watchdog packets. It should be up and running now. So see if it shows up on the door yet. So it should eventually show status out to the cloud service eventually. Okay, probably not going to do it. Let's see if we can, come on, got it. This could be a little slow at times. Anytime you start up a device, it usually takes a while to sync to the cloud services. I'll do that. Oh, that's it catching up with me hitting the keys. It's a little slow. The screen lags my device. So let's go give it a minute. Any questions at this point? This here, this running here is the application Akheron proxy. It's actually capturing data coming from one side, processing it for display for us, and then sending it on. So the device is fully functional right now, just hasn't told the cloud yet. It's still barking at it. We'll see if it comes up here in a second. What's in that? This is, let me see. There's a MAC address in here somewhere. Still. Yeah, the MAC addresses are always going to be in the interchip because remember, it comes down from the cloud, it hits the primary processor, sends it over to BLE processor. The BLE processor needs to know who to do. A single device in some cases, like a door lock, you typically can't pair multiple door locks to the same app. It's usually one door lock or one device per hub. In this particular case, it's actually, this device is a device, okay? It just shows position of the actual device. So you can see every time I do this, there it goes. You can see door with the closed. So it's actually opened. So it's trying to catch up. I'm getting a little bit ahead of it. But if we look here, see, you can actually see, okay, it's closed now. Still has it open or closed. This is funny. I hate that delay. It drives me nuts. Okay, now it just went to open. The way I hold the thing, if I hold it like this, it won't register properly. But if we look at here, here, let me hold this. So with the Control C, one Control C, we can take it off mode. Most of this is general handling data. I'm trying to figure out what these should address, but the CD45, this up here, that should be the MAC address, I believe. So yeah, this is very common. You're always going to see that interchip comms. Yeah. Now, the craziest thing I ever did, I was doing this testing on a device, and when you interact with your mobile app, it was all BLE, but then the actual hardware, the bridge was talking to it, there was no BLE address in there. And I'm like, I'm dumbfounded. How's this thing even know to work? After some research, I found out that it wasn't BLE, it was actually communicating with. It was another, oh gosh, what was it called? No, it wasn't Z-Wave. It wasn't that. It was actually a 2.4 similar to Bluetooth, but no, those are not even the same protocol. But it's almost identical to BLE, but actually, I won't remember the way I'm saying it to people. The protocol actually uses a completely different addressing method, but it's used for fitness equipment and Fitbits for fitness equipments. ANT, that's it, ANT. That one drove me crazy. I'm like, well, what is this? This isn't right. But I eventually figured out it'd be ANT. And the reason why ANT is an ANT in a particular case is because another device can connect to it. Can have one connection and multiple connections. By BLE being ANT, you don't have that conflict in that particular case. Okay, so now we're back open, and if we put this back into watch mode, we close the door, see the close come through there. And that'll eventually catch. That always lights my display here. And of course, my device decided it wasn't connected to the Wi-Fi again. Typical problem. I'm not sure how much demo we're going to get in here. I figure I'd come to a hacker conference. Probably someone's attacking my my MiFi. Let's cycle again. See what we can get. See if it'll come back. Because I want to actually show the capture mode. I can show the capture mode without it, but I was wanting to show the replacement. See, we have the ability to tell which direction the data is actually flowing. We also have the ability to capture this data. And of course, it's not working right now. I think my MiFi went down, attacking it. I should have figured that one out. Okay. So to save this problem, I think you've seen the tool. It works pretty good. But let's go ahead and bring out play this video. This is when MiFi is not working. So I'm going to go through here real quick, and we can walk this fairly quick. We've pretty much done all this. Let me jump ahead a little bit. It's trying to connect up. Bluetooth is connected. We'll run with the video here. So we jump forward, we can actually capture. We can do capture start. So at that point, transactions I carry out on the device, takes place on the device, actually get captured. What I'm running through is a couple cycles here. So I'm taking the door from open to close a couple times so we get it in both directions. So we take watch mode off, and then we have the ability to do capture stop. So you want to stop that so it doesn't continue. At that point, we should be able to do capture dump and see the actual capture if I spell the name right. I think I wouldn't do that in a freaking demo video, you know. I redid this video like 4 times for stupid mistakes like that, and I said, screw this, I ain't doing it again. Okay, so we're able to actually dump it. So if we look at these different ones, we try to find the direction and try to map these things out, looking for certain sequences that I'm familiar with. Like that one right there, that is actually, we come over here to 0101, that should be, I believe, an open, the door. 001 is a close. Right up here above that is the actual MAC address, 8DCD451E70. That's the actual MAC address for the end device. So that we know that is that, and I believe this one was kind of weird because it actually shows 2 of them, 5 and 9 as open. Anytime a device actually says your status or gets a command or gets information, you have to do it multiple times if you get the right response back. So actually see the command, make sure that the command makes it out to the actual device and the services. So we're actually going to replay dump 1, and we're going to replay. Okay, we're going to do help replay so we can show you what the help command is. So you can replay the entire file, both directions. You can also replay specific number because they're all numbered, so you can pick whatever direction you want to go. So it gives us multiple capabilities to replay things. So we're going to replay dump 5. So it sends that out and the door opens over here. So we're actually able to replay it in circuit. I think on one of these things, you're fighting the actual device responding on its own. So if the device is actually closed and you send it open, the cloud will go, oh, it's open. But then the device will say, no, I'm not, I'm closed, and it'll instantly close back as it did there. So some of the key values of having this kind of control is, not only do we have the chance to understand the end of security, we need to launch attacks against the end device and cloud services. So how this device is processing cloud services, we can pretty much inject what we want, and it's going to get delivered to the cloud. So there's a lot of testing, a lot of fuzzing can be done that way by sending who knows what kind of craziness into the cloud that you may want based on what type of device it is and how it functions. I see it potentially a way to inject exploits in there. I think I did a close on that one. Remember, I may have went to open and close. So the door's closed right now. I believe 27. That was one interesting thing on here is the serial number 27, because normally you get 26, and I remember I was recording this, it kind of threw me off because it's normally 26. But I think, where's it at? It's finding it there. Yeah, and that one's 27. That should be the actual open. Now I forced the lock to close. Now I'm going to send an interchip command here, and it's going to actually open the device. And this data is actually going to the cloud. We think about this, inside here, some kind of communications that identifies this particular device to the cloud. If you could get the control key that's associated with someone else's device because they were on YouTube, you could potentially start telling their cloud services, going, hey, here's this device, it's open. Just keep sending it open. The poor guy out, he thinks it's closed, now it's open, because you can lie to him. Now this one has a fairly minimal communication structure. But some of these are really complex, and a lot of complex data is actually sent out. And we'll talk about some other research that we're doing right now once we kind of get through there. So we did the replay dump, and I think we're working toward actually altering the data. Okay, so here is the command help replace set. This gives us the ability to actually set up a byte sequence that you've identified, a MAC address per se if you want to, and actually tell the device to replace it. I don't know why that keeps showing up there. There we go. So we're going to go ahead and we're going to do the capture dump, and we're actually going to set up a sequence. But what the sequence we did in this particular one's not complex. We're actually going to say, hey, when you see an open command or you see a close command, send an open command when it's replayed, as an example. Now, this is not in the live stream yet. That's on the list of to-dos. One of the things we're in the process of doing is potentially rewriting the program. The guy I asked to help me with this is a true developer. So initially, we kind of rushed out to get the proof of concept, and he doesn't like that because he's a developer, and he wants to do it right, which I'm on board for. So we want to structure it, make it more modular, so we can start plugging components into this more effectively. I'm also looking for people to get involved in this project, either through, oh gosh, you want that. Okay, so I was in the process of doing replace B. That's communication coming back from the device. Sequence I want, which is, I believe, close, and we're going to set it to open. The other one is open. So then when we go to replay it, the open, we're going to replay the open or the close command. It's going to give us the open command, or open command. It's going to give us a close command. I think you get the gist of it. We have the ability to alter this data. So let's go ahead and, because we got 10 minutes, and I want to jump over to slide deck. We will let that go. So let's go ahead and jump over here. Methods to the madness. So what are we trying to accomplish? Besides trying to understand that, can we weaponize the system? I think I look at chip comms. Once we understand how a device works or work, the potential of actually passing bogus data or incorrect data in here to either affect cloud services or target the end device becomes real. Instead of, in our case, I've done it like I did for one work in some cases. The mechanism's flawed. In these particular cases, there was a level of complexity they put in there. But with enough samples, just like we did with the encoding of the MAC address, if we got enough samples from enough different devices, it's reasonable to break that. And at that point, game over. Then we're able to control these devices. Future, what do we got planned? So we want split screens. So the screen looks good. We want split screens. Maybe we want color. We want to get a more graphic user interface, which is what I want to see. So we're going to expand these features. And what we expand these features is getting from the what would you like? What would you say? Play with the tool. It's simple. The hardest part, freaking hook it. Getting that in your head. I'm cutting these runs, I'm routing it out to a board, and I'm plugging the right things into the right things. Because I tell you, when I first started doing this with the whole concept, I'd spend an hour going, damn it, damn it, damn it. And I'd eventually go, okay, now I'm in my head after times how to plug it in. So that's probably the hardest part. Yes, sir? Yeah. So the whole smart thing, okay, let's start with the infamous smart lock, okay? If I want into your house, I'm going to do it with a crowbar. The convenience.
I'm not worried about someone coming to my house with your or our skills trying to be smart with a lock, right? I'm worried about the script getting defined the tool that then unlocks the metasploit, plug in, and now it's on.
Yeah, I kind of get it. To me, I'm more concerned with cameras, privacy. Privacy is more of an issue than the overall security. So we want to explore other interchip comms. What does that mean? I mess with all of these. This one's, I think, is the coolest, the high-speed USB. It's really cool stuff. We're starting to see more of that. I've seen that mainly on cellular-based technology. But for the most part, cellular-based technology still use UART because most of the vendors don't implement the high-speed internet for USB stuff. So I'm actually working on interchip communications for cellular-based devices. So this is kind of one we got set up here. This one was really bizarre because I wanted interchip comms between the cell module and the actual communication in the cloud and the main processor, because there's typically a main processor of some type that communicates with the cellular module. And it turned out that they actually did a voltage translator between the two. One side's 3.3 volts, the other side's 1.8, which really screwed me up. And in this case, I literally had to cut into the circuit boards to find the runs into multiple layers and remove chips to get access to do that. So that was kind of a crazy example. So, any other questions? Did you find this useful?
Wireshark for UART, right?
No, I'll tell you what we kind of envision. This is way down the road. A burp suite type technology for your interchip comms. Now, we are far from that. I think this is way more complex than capturing web traffic. But nonetheless, our goal is to take this to some usable level so researchers and testers have another useful tool if they want to do this type of stuff. Yes, sir? Oh, wow.
Yeah, no, that's a 140-year-old building that
Right.
But, yeah, I was wondering if this could plug anybody as sort of a filtering tool, because it was actually causing so much, the problem wasn't at the antenna, the problem was when it reached the messenger actual, and it couldn't handle everything coming in, so it didn't quit.
Sounds like a bandpass filter issue. Yeah, I haven't messed with that type of stuff in a long time, but bandpass filters to take, because you have your frequencies that are clean and coming through. Anything outside of that is noise. So if the device isn't capable of filtering that noise or properly filtering that noise, it doesn't make it through an application. Yeah, the fire control panel is the problem.
Last question was TPM, the AMD TPM exploit that just came out like this week. Looks like those guys are doing very similar.
Exploit I haven't seen it this week. One last year or the year before that, where they're actually able to capture the keys through interchip comms with the TPM. And this really comes into how circuit boards are built, because all those TPMs still need to communicate to other devices on the board. And if you're not doing that in a secure manner, that's a bad thing. So somebody in that case would need to go, hey, you need to design your circuit board, go to multi-layer, make it more complex, put it in sub-layers. That makes the attack vector more minimal. Doesn't take it away, because as you've seen, I've literally, with a scribe and a microscope, cut down through multiple layers on circuit boards to gain access to. I've gone down through 4 boards. The one board where I told you I had to cut down, that one I just showed on the previous screen to get to, first attempt to cut down was a 5-layer board. Go all the way through the board. If I would have cut up from this side, I would have got it at the second layer. So it was like 6 layers. So I had to go to 4 down layers before I got to it. I'm like, you're an idiot, Deral. Just flip the freaking board over.
When you're doing this sort of research and kind of things like voltage changes and procedures that are in line, are they doing that out of a matter of technical?
No, what it is they go, hey, we just bought all these devices for $1.90 each. We could buy this device for $5, but with $1.90 we can put a resistor or voltage translator for 10. So, talk about what's available. Design not all compatible with each other. You're going to have and stuff. Impede voltage translator. So,
have you encountered any sort of hardware security, hardware issues like product? Is everything fixable with software now?
heard anyone say everything fixed with software? That's a new one. Sure, it's fixable. Everything's fixable. It's all hardware fixable. Sometimes the design's just horribly bad, or they design something so the firmware can't be updated. Storage of data is fixed. So if you have a vulnerability in something that can't be patched, the only fix is reduce the hardware. It's the dream.
But do you imagine a burp slash metasploit in that future, right? Because if enough of these components are always labeled nonsense, right? Like modules,
Right. When you start getting into Metasploit, obviously I work for Rapid7. This is not an official Rapid7 project, even though Rapid7's the stuff is. We at Rapid7 are very big on open source and supporting open source projects. So even our employees that do research with open source ideas, we encourage them to do so. And this is one of the examples of the research. This is the see. You can download that, give us feedback, find bugs, let us know. You find security vulnerabilities, not a security product. A Rapid7's fault. The other thing is, this is a research paper I released on all of this. It kind of details the stuff we can't cover in an hour. So please check out the paper. I think it was kind of freaking cool. It was fun to do. And this has been going on for several years, and we're always finding new avenues to leverage it and support it. But we haven't really done any major software upgrades yet on the product. I'm trying to prod Matthew into, hopefully he sees this video. Matthew is taking it to the next level. I'm not a developer. I could do it. I could make it all work. It'd look really cool, but oh my gosh. Thinking it goes together by a 6-year-old with crayons. And I don't think I want that. That's not acceptable. Thank you very much. I hope you enjoyed it and got something out of it.
Thank you, Deral.